Good morning, friends. I'm Dr. K. Muralidharan, a professor of statistics working with MS University of Baroda. I'm also an internationally certified Six Sigma Master Black Belt and a quality trainer. Guys, before collecting data, one crucial question shapes everything. How many observations do we actually need? Sample size calculation helps us avoid too little data, which leads to weak conclusions, and too much data, which wastes resources. Let us understand how this balance works. The sample size refers to the number of observational units. The sample size can be calculated for some specific aspects, which you may call value of interest of the population. And that value of interest may be sometimes mean, proportion, variance, correlations, etc. etc. The procedure of drawing a sample from a population is called random sampling or simply sampling. Since sample forms the basis of all statistical decision making, it is essential to have a suitable sample size for any investigation. That's where we always trust for larger samples so that you get high precision estimates. Interestingly, the sample size calculation involves a lot of factors. That is, the first point is the type of data, which is discrete or continuous, accuracy of the data, and the precision allowed in the process. And if necessary, we can also include power of the tests, where whatever you are going to test in the whole process, and a small guess about standard deviation or proportion. For the guesswork, you can always go for range as an estimate for standard deviation or quartile deviation as an estimate for standard deviations, etc. etc. And finally, the most important part is the confidence level you are using in the calculation. Okay, so how confident you want it to be. So any sample is adequate if it provides an estimator with sufficiently high precision. So accuracy and precision plays a very important role in deciding the sample size. The measured value that has little deviation from the actual value is called accuracy, and is usually tested by comparing an average of repeated measurements to a non-standard value for the unit. And the mean, mode, median, etc., as you all know, they are called accuracy measures. So let us understand precision. Precision, let me denote it as delta, because I am going to recall delta everywhere. So it's how narrow you want the range to be for an estimate of a characteristics. For instance, estimate cycle time within 2 days, estimate percentage effective within 3%, etc., etc. So that is giving an estimate about how much precise you want your results to be. So it's actually equal to the half the width of the confidence interval. For instance, if 95% confidence interval is given as 48 to 52, and the total length become 4, so just divided by 2, that becomes the precision. So standard error is a crude measure of precision of an estimate obtained from a sample. So many often you can consider that itself as a precision measure. So you can also see that delta is going to be inversely proportional to 1 by square root of n. I'm going to give a justification to that. To improve precision, you need to increase sample size, which incurs more cost. So let us understand how precision and confidence interval are connected. So here are a few statements about processes, and you can see how the confidence interval plays an important role in deciding the process mean, variance, maybe percentage effectives, difference of means, etc., etc. So in all these, you can see that you are allowing some precision by default or maybe by natural sense. So okay, you may also say that precision is a margin of error admissible in each situation along with the characteristics of the value of interest. Okay, now I'm going to connect the idea of sample size with the precision and confidence interval. So let us recall a 1 minus alpha 100% confidence interval for population mean as 3842. As you all know, the formula is actually x bar plus or minus z alpha by 2 sigma by root n. Okay, which is from a closer look, you can see that is actually mean plus or minus precision. That's what exactly we are talking about. So you can also see that precision also involves two different components. That's one component is the critical value, and the other one is the standard error of the estimate. So the delta can be easily calculated as the difference between half of the difference between upper confidence level and lower confidence level. So in all together, you can see that precision is a function of sample size, critical value, and standard deviation of the process. Because standard deviation, when you compute standard error of the estimate, so standard deviation naturally comes for that. So a more precise estimate means a narrow confidence interval. So in that case, your estimate will be more precise. Once again, recall the 1 minus alpha 100% confidence interval for mean as x bar plus or minus z alpha by 2 sigma by root. So if I say that z alpha by 2 sigma, if I assume it as a constant k, so then you can easily see that delta, that precision is going to be inversely proportional to 1 by square root of n. So the knowledge of precision can ease the calculation of sample size, that means. So, and if you assume delta to be very small, so you will get a more precise estimate. Naturally, the accuracy also will be increased in that sense. So as said, there is no clear-cut answer about how much precision you need. The answer depends on the business impact of using the estimate. So each situation is unique and should not be influenced by someone else's decision. So don't make it a customary point that everywhere, every situation, the precision will be like this. But you have to decide what is the demand of the situation. And also note that to improve precision, you need to increase the sample size. So let us understand the sample size calculation for various characteristics of interest like mean, proportions, etc. etc. So here is the formula. As you all know, the 100%, 1 minus alpha 100% confidence interval for mu as x bar plus or minus z alpha by 2 sigma by root. So from here you can identify the value of delta very easily, and rearranging the term you can get the value of some sample size formula here. So for given alpha a value, say for instance alpha is equal to 0.10, you get the z alpha by 2. That's the critical value, point value from the normal distribution table as 1.645, and alpha 0.05 it is 1.96, and 0.01 it is going to be 2.58, very common and a universal value. Similarly, you can get if the characteristics of interest is proportion, then the sample size formula is going to be like z alpha by 2 whole square p cap into 1 minus p cap by delta square. So p cap into square root of p cap into 1 minus p cap by n become the standard error of the estimate. Okay, here are the tables for sample size, for mean and proportion. So you can see that for various levels of confidence, the sample size values are computed, and that too for given precision levels like 1, 2, 4, 6, 10, and for fixed values of standard deviation 5, 10, like that. So, okay, for both mean and proportion. For proportion, we have assumed different values of p. Okay, so getting a guess value for S may not be difficult. If you have a pilot survey, pilot samples, then you can get the sample values, sample standard deviation from that. So that can also be used instead of fixing the values like this. This is for convenience. I have fixed the values of S deviations. Okay, here are a few sample size calculations for mean and proportion. Okay, so look at the first example where we have assumed the precision as within 1 minute. So accordingly, the formula, the same formula which I had shown you in the previous slide. Okay, so 35. So you see the difference in the second example. The sample size increases drastically if you increase the precision. So if the instead of 1, if you make it 1 by 8 minutes, so the sample size shoots up considerably. Okay, so that is always possible. So if you ask for more precise estimate, definitely sample size also will be, and vice versa. If you increase the sample size, naturally precision will also improve. In the same way, you can see the an example for proportion. So here again, the proportion, in the first case, it is 0.05. And when you increase the precision means you are decreasing 0.05 to 0.02, you are decreasing actually. That means you are improving the precision. In that case, you will get more precise and sample size increases. Okay, so here is the sample size for difference of means and proportions. Because if your interest of characteristics of interest is difference of means, definitely you will have to change the formula. So note that I have fixed the value of n1 and n2 equal to n because there are two samples. So if you have different types of sample, definitely the formula may not be, implicit like this. So you may need to. So that's the reason why I have fixed the value of n1 and n2. Okay, so Look at the confidence interval. From there, you can directly identify the value of delta. That is z alpha by 2 square root of that. So n can be simplified to be this way. It's a very common and very generally used formula by you all. And as said earlier, for fixed value of alpha, 0.10, 0.05, and 0.01, you can get the value of z alpha by 2 and simply plug in. The same way, look at the formula for the character of interest is proportion. Okay, so you have n1, n2 equal to n is again fixed. And from the formula, you can easily identify the precision delta and rearrange the term, and you get the formula for n as well. Okay, so here is an example for both difference of means. So look at that formula. Sigma 1 is given, sigma 2 is given, alpha is also given, and even this precision is also given. Okay, so accordingly you get the value, say n equal to 47. If you increase the precision or decrease the precision, accordingly you will get the sample size. So naturally, the delta value is less than 1.2, naturally n will also increase. And if you increase the value, say 1.2 to 1.5, for example, definitely the sample size will be less. The same way, the characters of interest difference of means, you can get the formula on the right side. You can get the value of sample size as 51112. Okay, so many often people also use power analysis for sample size. Okay, power analysis is a simple thing. You can, if the context is, say, for example, testing or hypothesis related along with estimation. So the previous formulas are all for estimation purpose only. So if you want to include both testing as well as estimation as well as testing, definitely you need to go for the power analysis based sample size calculation. And here is the formula for difference of means. And here is the formula for difference of proportions. So these formulas are also very common. And many of the social scientists and life science people use this kind of formulas because they generally go for estimation and testing simultaneously. So while designing experiment, that's why I told the context is different here. While designing experiment intended for testing statistical hypothesis, one should consider both the desired level of significance and desired power of the test 1 minus beta, the sample size calculation. That's very, very important. So alpha is your probability of type 1 error and beta is your probability of type 2 error. Here is the examples based on both difference of means and difference of proportions. So for various choices, and you can get the sample size calculations. You can fix either alpha sometimes, you can fix beta, or you can fix in both alpha and beta together also, you can get the value. So many often people ask, is there any thumb of rules for sample size? I would say to some extent. Okay, so formulas for average and proportions we have already seen. In the formula again, if you replace 1.96, many often business people generally use 1.96 rounded off to 2. So in that case, there is nothing, I mean, nothing wrong in doing that because it will increase only a couple of samples. That's always fine. So it's always info because more the better. If the sample size is more, so definitely you will have the more precise estimator. But this 1.96, I mean, approximated 2 will not yielding too much samples, only a couple of samples. That's fine. And for frequency plot, generally, we always wanted to see whether the process follows normal or not. So in that case, we need a good sample, at least 30 plus samples. So 50 sample is ideal. Pareto chart again 50. Scatter plot and control chart, we may not require a huge sample. A sample of 24 or 30 or less than 30 is enough. So kindly look at this book, Six Sigma for Organized Excellence, written by me a few years ago. And it's a very good book for business and professionals working in Six Sigma and statistical consultants. And this book is really a good one. And you can see that there is a full chapter on sample size calculation dedicated fully on that. So please see that book. Okay, so okay, so also stay tuned for more videos on the channel, elucidation and interpretation. Thank you very much.